All right, here we are on the very last, or at least of week three, last big idea, sampling distributions. And this is kind of why we did all the stuff previous to this. It's all kind of building towards this with the binomial, the normal, all of it, probability distributions. It all comes down to sampling distributions because ultimately what we're going to be able to do with the idea of a sampling distribution, and this is a central idea in all of inferential statistics, we're going to be able to use what we know about sampling distributions to estimate parameters. That is, for example, if I want to estimate a population mean by collecting a sample and calculating its mean, I'll be able to do so, but not just give the estimate, but I'm also going to be able to give a margin of error for that estimate, as well as a level of confidence of how confident that I am, how confident that I am that the parameter lies within the margin of error of the estimate. Okay, so that's one thing. The other thing we're going to be able to do is hypothesize what a population parameter is. So for instance, again, I am going to, make some sort of claim like the average height of a person or male between the ages of, 20 and above is a certain height. What I'm going to be able to do is support that claim. Okay, I make this hypothesis, if you will. This is termed hypothesis testing, and I'm going to be able to, based on my sample mean, have some level of certainty, of whether to either accept that claim I make or to reject it. Okay, and so we're going to use probability calculations to do that. Okay, so we're either going to accept that claim or reject it based on a probability. And it's all going to revolve around the probability of, how likely it was that we got the results in our sample. And that's going to be based on this idea of a sampling distribution. Now, that probably didn't make a lot of sense to you, but hopefully we'll be able to refer back to that in the future. And when you start putting all these pieces together here to do some of these problems as we move through the course. But let's just kind of focus right now on this idea of sampling distributions and know that it's going to be important or a foundation for what we're going to do in the future. So a sampling distribution, a sample means basically takes, is a distribution that uses the means computed from all possible random samples of a specific size taken from a population. Now, just to show you how many there is, let's suppose I had a population of 1,000, okay, and I took samples of 30. Now, every possible sample that I can get from that, that would be every combination of 30 from 1,000 things. These were things that we did in week two, okay? This was a computation we did. Do that on the calculator. I get 2.42 times 10 to the 57th power. Now, that number is so big, we don't even have a name for that, okay? Or at least I don't know what it is to go out that many decimal places. But you could see that just in a relatively small population, taking a relatively small sample of 30 from it, you could see we have lots of combinations here. So just imagine if we had, millions of people here and taking samples of 1,000, how many combinations we would have with that. We would, I don't even think this calculator can compute that. Okay, so so that's we have a lot of combinations here. Okay, now what we're going to do here in this, simulating a sampling distribution is we're going to actually approximate the sampling distribution. Okay, and I'll emphasize that as we get through, but I wanted to address this first. All right, so let's just suppose I have this huge population here, okay? And this normal distribution is going to illustrate that. I just have thousands and millions of observations here. And the average of all of them are 10, and the standard deviation is 2. Now, if I go ahead and take 30 out of there, okay, I can use Staplet to do this. And I kind of cut these up here. I'll go into the software here and do it real time for you here in a second. But if I take 30 out, just like it does here, calculate the mean, and then throw it in to this group right here. Okay. And I keep doing that over and over and over again. I get another 30, calculate its mean, get another 30, calculate its mean, record it down here, another 30, record its mean down here. And I keep doing that over and over and over. Let's say I did it 1,000 times, and the software is going to be able to do this very quickly 1,000 times. This is going to be the distribution of all the X bars. So this is the distribution of the individual, and this is the distribution of the X bar when I take 30 out and record its mean over and over and over and over again. Now, I only have 1,000 here. How many, if there were 1,000 observations here and I were taking 30 out, that's how many combinations. I don't have enough time to wait on to do that. And the software, I don't think would be able to do it. Okay. It would just, I don't know if it would crash or just get tied up for a long time, but that's a lot. Okay. So we just did 1,000. So this is really the approximation of the sampling distribution. All right. But what we're saying is that what that pattern is going to be. Well, let me just show you how that works here real quick here. So if I got into Staplet here, okay, let me reset all of this stuff here. Reset everything. Okay. So if I do that, okay, and Staplet does it, you can, like I said, you can do this very easily just by getting into simulating sampling distributions, but they only give you one option here with 10 and 2 for means and standard deviations. So if I select the sample here, that's how that does that, okay? You can see that it takes 30 out, calculates the mean. So here are all the individuals, these were all the individual observations right here. I'm just going to scroll over them. You can see their values at least to 3 decimal places. And it calculates the mean of all 30 here, and I get 10.5, and it plots it down here. And then if I do another one, okay, notice I got another 30. Now this mean was 9.6, and it plotted it down here, okay? So if I want to quickly add 998, to get my count up to 1,000, and I select them, that's all I did for that, okay? And you can see that I roughly got what I got on the screen, on the other screen here, 9.978 and 0.365. That's pretty close. No, I guess not that close, but pretty close. Okay, so that time I got 3.8, all right? So you get the idea here of how that works, okay, this in terms of the simulation. So what we're going to take a look at is the central limit theorem, which basically says this, is that if I have, and I could do this with some other population, I'll go back and do this live time. I had here, I always use this, this is again from my other course, any old way, which means it can be any distributed. It doesn't even have to be normally distributed. But what I'm going to say is that if I get the X bars out of there, then the X bars are going to follow a normal distribution where the mean of the population is going to be the same as the mean. The mean of the X bars is going to be the same as the mean of the population, and the standard deviation of the X bars is going to be the standard deviation of the population divided by the square root of n. Okay, so I did that over here. I took the standard deviation divided by the square root of the sample size, and I got about 0.365. And notice we got something pretty close to 0.365. As a matter of fact, when we did it down here, it was 0.365. Okay. So, we're going to get something close to that. And obviously 9.95 or 9.978, like we did down here, is really, really, really close to 10. Okay. Now, why is it not exact? Like we said, we're going to get here. Well, it's not exact because we don't have every possible sample. Okay, we only got about 1,000 of them. All right, and actually the central limit theorem says, because we're not always, sampling from a normal population. Okay, that I'm going to go back and do that over here. It could be from a skewed population. Okay, and we're still going to have the sample means be approximately normal. Now, how normal will the X bar be? Well, if it comes from a normal population, then these are going to be, really close to being normally distributed. Or actually, if it comes from a normal population, they'll be exactly normally distributed. But if they come from something that's skewed, it's going to be approximately normal. But as long as these are rules of thumb, okay, And I can put these in here basically as the sample size goes up, then the X bar becomes more and more normal. And the standard deviation obviously is going to decrease because I'm dividing by a larger number. So if it's not too skewed, the population, as long as I got sample sizes of 15, I'm usually good. And then if I just have 30, okay, if I just have samples of 30, then that's going to be great, even in spite of these strong skewness. So I'll just go ahead and illustrate that back here. I can mess around with these sizes here. So let's just say, first of all, let me go ahead here and reset everything. And I'm going to go ahead and do that. And so now let's take something that's a skewed population. Okay, so that's definitely not normal. All right. And I'm going to just, that's pretty strongly skewed. So let's say if I got small samples here, okay, and then if I get another 998 of those, I'll just put in 1,000 here. You can see that I got some skewness here. Okay, it's kind of normal, but we can see a steep side here and then starts to spread out. But if I go ahead here from that same population, and let's just say I take, I'm going to clear my samples out here, and let's say I get 30 of these, and I go up to 30. Okay, and I could work my way up, but I don't want to take too much time doing that. And I select 1,000. Now you can see that skewness starts to go away. And it'll really go away if I go over 30. If I clear my samples out here and I select 1,000 samples here, because the sample size is so big, remember the standard deviation is going to cut down, but this becomes more and more normal as we get larger and larger sample sizes. Maybe if I were to went to 50, we might get a little better. This isn't going to get so the standard deviation will get we could see it a little better. It's a little bit more spread out. Okay, it's going to get real skinny with a large or a small standard deviation. All right. So even if these data are skewed like this, or the population skewed like this, notice if we calculate the means, they're still going to be pretty close to the mean of the population here, which is 3. I'm going to get some extreme values here, obviously, but that's kind of nullified because of the sample size being so large. All right. So we get back to this. As long as we follow these parameters here, we're going to get these means being normally distributed. And that is a big idea, okay, that we wanted to get to here. All right. Real quickly here, and like I said, we'll see the application of this and problems here coming up with the ALEKS problems, but I just wanted to have this as a reference point just so you can see where this is coming from and why we can use the normal distribution. And I'll refer you back in those videos just in case you didn't see this the first time. But we also want sampling distribution of p hat or a sampling proportion. And I'm just going to give you the formula here. We could do an activity similar to what we did on the other one, but it's not in Staplets. So I'm just going to give you the end result. And that is that, again, if these conditions hold, okay, sometimes it's called the 10%. If my sample size and my, P here, my probability or population proportion is, if I take and multiply those together and I get something greater than 10 or equal to 10, and then take the sample size multiplied by 1 minus the population parameter, and that's also greater than 10. And if the population is greater than 10 times the sample size, then these sample proportions are going to follow a normal distribution. Okay, so again, I just want you to see that there's also a similar pattern here, but the big thing is that we're using this normal density to model these things. Okay, so we can model individual observations, and we can also use a normal density to model the distribution of sampling statistics when we take a statistic. And remember, we're going to apply this to more specific problems that are very practical and applicable later on, and this is kind of the foundation of it. these two big ideas here, the sampling distribution of p hat. By knowing this, we're going to be able to answer some questions in the future that are going to be very practical and useful, and also the sampling distribution of x bar. They both follow normal distributions, and that's why we spend so much time studying the normal distribution. Okay, so there's your last video for the big idea for week 3, and I'll be back with some more specific ALEKS examples as we go through the rest of this week 3 material.